Can start recording. Okay, it's my pleasure to introduce Theodore Drivas from Stony Brook University. He will give part one of his mini course on mathematical aspects of turbulence.
Okay, so thank you very much for having me in this program. I guess I'd like to begin by apologizing because the program is about renormalization, and I know not very much about that, and even less about how people have used it in turbulence. But what I'll try to do is explain certain problems. First of all, what turbulence is or has been all about, and certain problems that I think bear similarity to problems in dynamics. So in particular, my first couple of lectures will be on classical fully developed turbulence theory, what we know rigorously and what we observe, and how to connect those things. So this will cover, well, I'll say in a second. My next two lectures will be more along the lines of dynamics. So I'll talk about the problem of transition to turbulence, and then the formation of small scales in inviscid flow.
So, when you talk about small scales, it means that you talk about renormalization. So it is,
yeah, so
maybe you hide it, but
I'm hoping that somewhere there's hidden renormalization and you'll be able to see it. Yeah. So maybe I'll start with a detailed outline so you can see sort of what's to come and what we'll do today. So I'll just start with some very basic properties of fluid equations for everybody to be familiar. I know there are many experts here, but just to be on the same page.
There are many non-experts as well, so please keep it in mind.
So it will be quite elementary, yeah. Then I'm going to talk a little bit about what this means, high Reynolds number, and talk about some behavior of fluids in that regime from experiments in numerics. And these are the things that guide theoreticians and mathematicians. And in fact, this is what inspired Kolmogorov's 1941 theory, which I'll describe at some length. And then corrections to this theory, areas where it could be improved in order to fit better with these experiments. So this is related to Landau's remark about intermittency. Let me say that I'm actually doing something, I'm sort of following the history, but also I think it's maybe a good way to understand the subject. I'm starting out with infinite Reynolds number. I'm talking about fully developed turbulence and what is seen there. What are the robust features when a fluid becomes more and more turbulent, some ideal setting. But then as I go on, I'm going to start talking about how the fluid actually gets to this state. So starting in my third and fourth lectures, I'm going to talk about this problem of transition to turbulence. In particular, there's a setup proposed by Kolmogorov called the Kolmogorov flow problem, which is a very precise setting in which one can understand bifurcations of stationary states and instability, and try to track this route to chaos in turbulence. So I'll talk about results there. And then finally, if I get to it, I'll talk about this formation of small scale structures in the infinite time limit of ideal Euler fluids in 2 dimensions. Okay. Okay. So we'll start, as I said, just reviewing the equations. So the Euler equation for an ideal inviscid fluid were derived, I think it was the second PDE to be derived. It was derived by Euler in 1757. And the basic state variables are the velocity, which is a function of a spatial point in a domain omega, let's say a subset of RD, and time, and a pressure field, okay? These equations consist of the following system. So there's conservation of mass, which in the incompressible case takes the form of just the divergence of the velocity field being 0. That's the sum of all these partial derivatives being 0.
Theo.
Yeah.
What do you mean? I think I know what I mean by a velocity field. But what do you mean by a pressure field?
I mean, so I'll explain a bit more about the pressure momentarily, but it's a scalar field. And in the incompressible model, it's essentially a Lagrange multiplier that maintains this constraint that the divergence be zero. It's a physical pressure, so I'll explain in 1 second, actually. So in the other equation or system of equations that complete the system are conservation of momentum, which read as follows. So this is mass density, which is taken to be just a constant in the incompressible regime. The rate of change of the momentum is some nonlinear term that I'll explain more in a second, and a pressure gradient. So the pressure is an...
I guess what bothers me, why have the word pressure in there? It just familiarizes yourself with the way people talk about it, but logically you're saying it's a mathematically derived field that enforces some constraint. So why call it the pressure? Or
well, I call it the pressure because it acts as if you think of a little volume of fluid, it acts as a force in that volume of fluid the way a pressure does. So it's resisting contracting that little element of fluid down. Yeah.
Well, you can also compare it with equations of continuous media, where there is all sorts of different models. And this would be just a particular instance of one of those constitutive tensors, I think, that come in those models. So it makes perfect sense to see fluids in the equations of fluids as part of the continuous media equations.
So, sorry, can I ask something?
Sure.
Do you have stresses in this flow?
Yeah. So at the moment, the only stresses are you can write this equation in divergence form, in which case you have a stress tensor that involves the nonlinearity and the pressure. Later on, I'm going to introduce a viscous stress, which is going to be part of the Navier-Stokes equations. And those are all the stresses I'll consider for the remainder of the lectures.
Thanks.
Okay. So Dennis, of course, has a correct point here, which is that this pressure is not doesn't correspond as is usual in a thermodynamic system to some given thermodynamic function of other state variables. Instead, this pressure is really just ensuring that this mathematical constraint on the velocity field u is maintained by this equation. But nevertheless, it acts as a pressure force in the way I said. Yeah.
well, I don't really understand that. I mean, maybe P stands for potential. I mean, the previous remarks haven't explained. They're using terms that have come forward, and you use the terms as part of the explanation. So, I mean, I'm just unhappy. I mean, I'm just unhappy about it. I mean, P maybe stands for potential.
Okay, well, in any case,
I mean, what do these words pressure and stress mean? You have to say what they mean.
So in this case, the pressure means just exactly what I said, just something that ensures that during the motion, this constraint is propagated.
Okay, and you just choose to call it pressure, which
Yes.
has other intuitive meaning. Okay, because of some analogy.
Right. Okay. So these equations are, of course, supplemented by initial data to complete a Cauchy problem and boundary conditions. So the boundary conditions typically are either that you are periodic. So you say you solve this equation on a flat torus, TD, or if you have a physical boundary, a natural condition is that the fluid be non-penetrating, so that at the boundary, the velocity is tangent. Okay, so this is the normal component is zero. Okay, so now maybe we can just understand a little bit what this equation is saying from the point of view of a fluid particle. So let's just consider the position of a particle x of t that started labeled at a point A and is just moving along with the velocity field u. all this equation is saying is that the acceleration of this particle, or rather the mass times acceleration, this is a constant, is equal to the gradient of this function P, the pressure, what I call the pressure. And this is just Newton's law saying mass times acceleration is force on the infinitesimal element. Okay. This incompressibility constraint here, divergence free, is reflected in this picture by the statement that the volume, like an infinitesimal volume of fluid parcels, is preserved. So the determinant of the gradient of this flow map is given just by this exponential of the divergence, and that's 1. So volume is preserved by the flow. Okay. So these equations are a complete system, but of course you have derived conservation laws from them. Okay, and I'm going to just say now the most basic one, which is a conservation of energy or kinetic energy of the flow. As you know, kinetic energy is mass times velocity square. Here you're integrating over the domain. And if you just take the equation, multiply or take the inner product with the velocity field u and integrate, an elementary calculation using integration by parts shows that the entire contribution of this is a spatial flux, which ends up being just some integral on the boundary, over the boundary. And then using the fact that the fluid is non-penetrating, or if you have periodic boundary conditions, this contribution is 0. So kinetic energy is preserved, at least if the motion is smooth enough to justify these manipulations here. And we'll talk at length about this point later in the lecture. Okay, are there any questions so far? Okay, so maybe we'll just, I guess this was already said, but we'll reiterate it. So this thing that I'm calling pressure is really just a constraint to ensure, as I said, that the fluid remain divergence free, the velocity remain divergence free. And so in particular, it's not given by some equation of state, but rather from the equation that you must satisfy, you derive a law for it. So you take the divergence of this equation, that gives you the evolution of the divergence, which starts out at 0. And in order for that equation to propagate 0 for that solution, you require that the pressure satisfy this elliptic equation here. So this is called the pressure Poisson equation. And thus, in this way, the pressure is actually given as a singular integral of some quadratic expression involving the velocity. Okay. Now, a very important object in the study of fluids classically is something called the vorticity. And again, this is an object that you derive from the equations and then investigate its properties. It turns out to have very interesting properties. So what the vorticity is it's just the curl of the velocity field u. So I've written it out here in terms of its components. Geometrically, the vorticity gives an axis and a strength of local rotation at each point in the flow. So it's somehow measuring rotational part of the fluid flow. And if you just use some identities from calculus, you can rewrite the nonlinear term in the equation as the cross product. Here I'm in 3 dimensions, by the way. The cross product between the vorticity and the velocity up to a gradient term, which will eventually be, you can treat that as part of the pressure. If you do so, and then you take the curl of the equation so as to derive an evolution equation for this vorticity, you find, again, using these identities, that actually the vorticity is just Lie transported by the velocity field. So as a vector field, yeah, you can identify it with a vector field in 2 dimensions, in 3 dimensions. So the vorticity satisfies this transport equation by the velocity. And this immediately tells you some interesting features Namely, if you have a vortex line, which is a line along which the vorticity field is tangent, then that line remains a vortex line if you evolve it under the fluid flow. So maybe the strength of the vorticity changes along the line might be bent, but the vorticity will always remain tangent. And this is just a consequence of this transport property of the vorticity in 3 dimensions. Okay.
Theo, just
Yes.
just a technical issue, just for the future. This red, when you write in red, it is poorly visible on the black background. Maybe you can use some other colors in the future. Because,
Okay. Okay. Thanks.
Do you know if there's a physical argument for the invariance of the blue lines?
Yeah, that's a good question. The only argument I know is really derivative from the equation. So I don't know of an argument based on physical principles alone to say that this property should hold. Now, other conservation laws of the equation, like mass and momentum, ought to hold for physical reasons and from the systems which approximate the fluid. So at the level of the particles approximating the fluid, mass and momentum will be absolute conservation laws and also energy, total energy of the flow. But vorticity is something that I only know how to see this conservation once you go to the continuum formulation in the equation.
Yes. But on the other hand, it's quite well observed, right? Would you say?
Certainly signatures of it are well observed, but typically in the real world, there will be terms like viscosity that need to be accounted for that make all these statements only approximate. So it is observed, but in an approximate sense.
Okay.
Okay. Now I want to make a brief remark here about 2 dimensions. Actually, most of the talk today and probably Friday will be in 3 dimensions. But in 2 dimensions, there's a certain simplification that happens with the vorticity that turns out to be extremely important for the theory there. So by a 2-dimensional flow, I really mean a 3-dimensional flow which has no vertical component, and the planar components are functions only of x and y, not x, y, and z. And for such a field, if you just look at what the curl is, you find that the vorticity is pointing out of the plane where the velocity is confined. And it has this structure, which is the perpendicular gradient dotted into this velocity, this 2-dimensional velocity vector. So it's a scalar, in particular in 2 dimensions, it's identified with a scalar, which is either pointing out or into the plane, depending on its sign. And moreover, because of this structure that the velocity doesn't have a z component, but the vorticity only has this z component, the 3-dimensional vorticity equation is just reduced to a transport, because in particular, this is a z derivative, so that term, which corresponds to essentially amplification of the vorticity, is no longer present. So this property, as we'll see probably next Wednesday, turns out to be a crucial part of understanding 2-dimensional flows. But for now, I'll leave it and we'll return to 3 dimensions. So I'm going to give one more consequence of the equations, which I think is in general too important to leave out, although I'll have sort of very little to say about it later. I might make some final remarks about its potential role in understanding turbulent motion, but I think there's no clear idea of if that's really true. But okay, so this is called the Kelvin theorem. And it has to do with the conservation of circulation of the fluid velocity along materially advected loops. So in particular, I take some closed curve C, and I flow it with the trajectories of the fluid. And now I claim that the circulation, namely the integral of the tangential velocity around this loop C, is conserved by the motion of the fluid. So here's just a picture. Here's the initial loop. The velocity is going around this way. You flow it, it becomes some distorted loop. The velocity is doing something else. But nevertheless, if you compute the circulation around, you have to get the same number. Just a remark, this is equivalent to vorticity flux conservation. So just by application of Green's theorem, you can relate the line integral of the velocity around the closed loop to the area integral of the vorticity flux, so the normal component through that area of any bounding surface. And then the statement is that the flux of the vorticity is likewise conserved by the motion. So this soap bubble type object will get deformed over the course of time, no matter which initial bounding surface you start with, this will be conserved. Okay, and another remark, which I think is very important, is that the circulation theorem is actually a characterization of a smooth Euler flow. So in the class of sufficiently regular velocity fields, the only ones for which the circulation is conserved in the sense above for every closed rectifiable loop are solutions of the Euler equation. So in a way, by saying just this statement, this geometric statement about the motion of these loops and their tangential velocities, you already say everything about the Euler equation. Okay, at least for classical solutions. Okay, so the proof is quite simple, so I'll just show it. You just take a parameterization of your initial closed curve S. So this is a periodic parameterization, C, periodic parameterization. And okay, from that, you get a parameterization, of course, of the materially flowed curve, xt of C. Now, this integral, if I write out what it means in terms of this parameterization, I'm just integrating over 0 to 1 of the dot product between u and the tangent vector to the loop, which is just this object right here. So now in order to show that this is conserved, I just take the time derivative. I get two terms when I differentiate this expression. I get one term where the derivative hits the velocity, and another term where the derivative will hit the xt. When the derivative hits the velocity, and I just apply chain rule, I get time derivative of the velocity itself, and then I get the time derivative of xt dotted with the spatial gradient of u. But that time derivative, as we know, is u itself, because this is a particle moving with the velocity of the fluid. So this term is just equal to this, as we saw before, the acceleration of the particle is just equal to this in terms of the fluid velocity, and therefore it's the pressure gradient according to the Euler equation. On the other hand, if the time derivative hit this x of t, I just directly use the fact that x t dot is equal to u, and I can write this as the s derivative of u. Now, this itself is just a total derivative in this parameterization, and this is a gradient as well. So this means it's a spatial gradient. And if you integrate a gradient over a closed loop, you get 0. And so this is the entire proof of the Kelvin theorem. And already, by the way, from this proof, you can see why it works the other way. If you were to know instead that the rate of change of this object is 0 for every loop, then you could reconstruct this gradient as the unique gradient that maintains incompressibility. So this proof actually shows, and just with a little additional words, shows the equivalence that I mentioned.
Right. I just want to add, you have to state the equivalence as volume preserving motions that have this property are precisely solutions. of Euler's equation.
Absolutely, yeah. I realize I didn't say volume preserving. That's true. Right. Okay, so everything I just said was for this idealized motion of a fluid where we didn't account for any additional stresses, as was remarked before. In particular, no viscous stresses. And there's this somewhat famous paradox, D'Alembert's paradox, which is that in an irrotational, so this is an Euler flow without any vorticity, that's called irrotational. So in an irrotational Euler flow, the drag on a body moving with constant velocity relative to the fluid is 0. This is a theorem you can prove about Euler solutions, but in particular, the implication would be, if you read it literally and you think of air, for example, as being governed by the Euler equation, it would say that planes can't fly in an irrotational Euler fluid, or birds. And the picture that's associated with this paradox is that the streamlines, or the flow lines of the velocity as they go around an object, here's a plane or a bird, are just this laminar picture. I mean, just accommodating the shape of the body. But in particular, the net force that it's exerting on that body is 0 by this remark. In reality, this is not what you see. And so what you see is more like the picture on the right. If this plane is going this way, then there's some sort of intricate interaction of the flow with the boundary of this body, and that causes a wake, and that causes essentially interaction forces between the body and the flow, and suddenly this paradox has its meaning, namely you observe this type of drag force on bodies in the real world. So it's paradoxical that the equations for the fluid wouldn't describe that.
So isn't the object moving? I mean, if we pretend the object is moving to the left.
Yeah. The object's moving to the left, right? Yeah. So a solution to this paradox, and by the way, in a certain sense, which maybe I'm not going to discuss right now, but in a certain sense, there's still a paradox from the point of view of pure mathematical understanding, but we can talk about that later. The immediate reaction to this statement is that one needs to account for frictional forces between adjacent molecules, and in particular, this would account for frictional forces near the boundary of this object. And these frictional forces are termed viscous forces. This is the effect of viscosity. And so along came Navier and Stokes in the 1800s, and they derived a model for how these frictional forces should be incorporated into these fluid equations, based on the assumption that this shear stress is proportional to the symmetric part of the velocity gradient. Okay, and under that assumption, the equations are the same as the Euler equations, except for the addition of this one term, which is the viscosity, something proportional to the viscosity, which is just a positive real number, times the Laplacian of the velocity field. So this is, for example, the heat modeling in the heat equation. Okay.
And your Laplacian is a negative operator.
Yeah, that's right. It's a negative definite operator. So I've included here an external body force because, at least in many mathematical setups, this is an important feature, and we'll discuss it at length in certain setups later. In the real world, actually, often the forcing is through the boundary. So it may be rare to have really a body force in the sense that we like to think about mathematically, but it can actually be arranged in laboratory experiments. So we can come back to that. Right. So this system of equations here, the Navier-Stokes equations, are currently a very well accepted model of so-called Newtonian fluid flow. So the word Newtonian here means that the viscosity is a constant rather than some state-dependent quantity. Namely, in a non-Newtonian model, the viscosity could depend, for example, on the value of the velocity gradient at a given point. But in this Newtonian model, this is just a constant. So this is sort of a very well accepted model for this situation. And in fact, there are some rigorous derivations of it from more fundamental models, I guess you could say, in a limit of very small Knudsen number, which is the ratio of the mean free path of the particles which the fluid is comprised of. So there are physical particles making up the fluid. It's not really a continuum. And at the level of those physical particles, you have an associated mean free path, which is essentially a distance measuring how far these particles are apart. And you have a gradient length, which is in this continuum approximation, what's the typical length scale set by the size of the derivative of that approximation in some norm perspective, some way to measure it. And so basically in a region or in a regime where the particles are interacting and sort of hitting each other at a scale much smaller than the scale of variation of the large scale field, that's a regime we call small Knudsen number. And then there's this other regime that's necessary to justify this model, which is the regime of small Mach number. And that's just the regime in which essentially sound is traveling infinitely fast. So it's a limiting regime of a compressible model where the flow velocity, namely the velocity of the fluid at any given point, is much, much smaller than the speed of sound. And so in a joint limit where these two parameters are taken to zero in an appropriate, precise sense at the level of the fundamental model that you're looking at, you can derive these Navier-Stokes equations as a limiting regime. And so there are a number of results in this direction. I'll just mention a couple of here. So there's a result by Quastel and Yao in 98 for a certain stochastic lattice gas model, where they derive this equation up to fluctuation terms. Okay. And then
HT Yao and not ST Yao.
Right.
I mean, Stony Brook, if you say Yao, they think ST Yao.
I see. And then there are results deriving these equations from the Boltzmann equation, which describes gases by Laura Saint-Ramon, among others. There's a whole history here, including Gauss, Livermore, Bardouche, and others, but I'll just mention this. It has references there. And then there's the point of view of molecular dynamics. And there's a beautiful book by Spohn, which describes progress in this direction. But as far as I understand, there's not an unconditional derivation of the equations from this viewpoint. There needs to be some additional ergodicity assumption at the level of the particles in order to justify things like the viscosity really popping up there. But okay, so from now on, essentially in the lectures, except for maybe the very last one, we're going to focus on this equation, the Navier-Stokes equations, and incorporate the effect of viscosity, which, as we've seen and will see, is very important for the behavior.
So, Till, what is the speed of sound in these models, in these molecular models?
So, right, so the speed of sound. So let me say it like this. I mean, this. If you think of deriving first the continuum model from taking a small Knudsen number limit, then you would arrive at some compressible fluid equation where there are additional state fields like the mass density and temperature or internal energy, as well as the velocity. And the speed of sound in that model is precisely just the characteristic speed of essentially linear density or pressure waves within that model. So it's mathematically, it's related to the derivative of the pressure with respect to the mass density. Square root of that is the speed of sound, and it appears as this characteristic speed governing the, just the motion of those density waves.
So you need to pass to some limit to define it, some continuum,
Yes.
continuum limit.
Yeah. That's at least the way I know how to define it. There may be ways to define it at the level of the discrete system that I'm just not familiar with, but.
Okay, thanks.
Yeah. Okay.
Well, it's something you can actually observe by experiment too.
Right.
You might think of it as a observable.
But how this observable enters the model? So how it is presented in the model? So that is the question.
Well, no, I mean, a model is a model of something, so you can observe the something, and then you would have the speed of sound to put in the model.
Well, so actually, I mean, in the compressible equation, for example, the speed of sound is certainly not something that's uniform. It can depend on the particular position and time, and what it's what it's given by is this relationship with the pressure, and so I don't know. I mean, that's the sense in which I understand the sound speed. I don't know how it would manifest itself in discrete models, for example. I'm sure there's some analog. I just don't know. Okay. So so now we come to this basic principle, which is that physical laws should be independent of units they are measured in, and so it's a natural thing to non-dimensionalize the system, namely to introduce some sort of characteristic scales and to measure things just relative to those. And so typically in this subject, we take characteristic velocity and length scales. So the characteristic velocity scale U may be something like the root mean square velocity, which is the square root of the L2 norm. I mean, it's just the L2 norm, square root of the energy. Or it could, and characteristic length scale L, which is typically the size of the container. So maybe the domain size or the period if the flow is periodic in space. And now all the terms in the Navier-Stokes equations have units of acceleration, so L cubed over U square. And if we non-dimensionalize by sending U to U over this characteristic U and so on, then Navier-Stokes equation is transformed to this equation where I just write U again, but we understand it as non-dimensional. Everything is non-dimensional. And out pops this number, 1 over the Reynolds number is what it's called, which is just defined like this. Okay, so now this is a non-dimensional number. And in a sense, it measures the relative strength of the inertial term to the viscous term. So whether inertial forces are dominating or viscous forces. And as Reynolds number increases, formally, if you set it to be infinity, then the flow is inviscid. And as we'll see, the behavior at large Reynolds number is both extremely relevant for many applications, but also it's extremely delicate. So the behavior in that regime can be a subtle and difficult thing to understand.
So, Theo, if we imagine that the fluid looks like the picture behind you,
yeah,
what would you say the Reynolds number is?
Well, yeah. So I happen to know that
500 or something. What would you say?
Yeah, this is on the order of 2,000, something like that.
The one behind you.
The one behind me. Yeah, this is a simulation done by a group that I know. I think it's on the order of between 1 and 2,000.
So 1,000 is sort of things start to get wild somehow.
Yeah, I mean, it's also very situation dependent in the sense that like the thing behind me is stirred with a body force, which is acting everywhere in the flow. But Reynolds numbers can be very high and look very different if you have some anisotropic system, like a plane moving through the air. Then the behavior of the fluid away from the plane, near the plane, behind the plane will all look very different. I would say that, yeah, behind me is something hopefully like behind a plane in a way, in the wake. So actually, here's some numbers just so you can have some sense of what these are. So typical Reynolds number at the scale of bacterial motion in a fluid is like 10 to the negative fifth. A typical Reynolds number in blood flow, like veins or arteries, is like 100. A Major League Baseball pitch is like 10 to the fifth. A wake of a blue whale, 10 to the eighth, and then Boeing wake, 10 to the 12th. So the Reynolds numbers increase as you go to larger scale objects that are moving faster, of course, because of the way it's defined. But the point is that if we want to understand certain physical scenarios, like the wake behind the plane, or even things at a much bigger scale, like supernova explosion, that type of thing, we have to understand the motion of fluids in a regime with very small parameters that multiply the highest order term. So this is a very singular limit, and it's crucial to understand it in view of these applications, in view of these scenarios. So I just want to make a small remark that in experiments, I mean, one often uses this so-called Taylor scale Reynolds number, which is defined just slightly differently. It's still some characteristic velocity, length, and viscosity, but now this length is defined by the gradient length of the flow. So it's you take the sort of, this is called the enstrophy, or just the square of the H1 dot norm. It defines a length scale if you divide through by it the energy. Okay, so this is just in terms of context. If you see this Taylor scale Reynolds number, it's something slightly different than what I defined above. And the typical situation is that this is much, much bigger than, so if you define it in this way, then the comparison between these values is shifted. So just for general.
So it's still dimensionless, right?
Yeah, it's still dimensionless. It's just the way you.
In some sense, this is the first Reynolds number is kind of more global, and this is more local. Would you say?
Yeah, I mean, I would say that this Reynolds number is somehow more flow specific. So you're not really the large scale length that you're using is something defined by the fluid velocity itself. So I think it's popular for that reason. It carries somehow more information about the behavior of the flow.
Oh.
Yeah. Okay.
Oh, wait.
So
wait, sorry. You get the derivatives on the bottom. So when the derivative gets big, this should get small. So you have it getting. Oh, that's lambda squared. Oh, with lambda. No, but that's the same thing. Yeah, okay. Lambda's on top. So the derivative is big. If very oscillating, then lambda is small.
Yeah, don't forget that this is an average quantity over the entire domain and maybe also over time. So this is not very sensitive to very small scale variations in U. Anyway, dimensionally, this is a length. So
what?
Length square. Dimensionally, this is a length squared. This is how you formulate. Yeah. Anyway, it's not so important for later. I'm going very slow, unfortunately, but so this is just some pictures. so you can see what it's like. So for relatively small Reynolds number, you have this von Karman vortex street, it's called, of these shedding vortices behind a cylinder. As you increase the Reynolds number, these are two cylinders now. You see this sort of turbulent wake developing. You increase it further, much finer scales emerge. And even further, in a different setting, you have this fine scales, but also spatial spottiness, which is a very important feature of turbulent flows that you can see here in this picture. This is behind a grid. Okay, so now I'm going to begin to talk about theoretical understanding of these scenarios. And to preface it, I want to first admit some of the shortcomings of what I'm about to say, and also to provide some, at least my perspective of the roles that different people attacking these problems typically take. So the first major thing is that, as I alluded to before, turbulence is typically generated by interaction with boundary and not generated by some body force. However, it's expected that features, averaged or statistical features of the flow, should be somehow universal away from the boundary. So, and also the behavior at very small scales should be universal away from the boundary. This is just expectation. So if we neglect boundaries and we think of some other idealized setup, the hope is that we'll capture, for example, the behavior of the wake behind an airplane in a particular regime. Also, generally speaking, given what we just saw about how complicated the flow configuration typically looks, it may be unreasonable in certain regimes to even try to make pathwise predictions about the fluid velocity field. So historically, people have focused on trying to predict averaged quantities, either over space and time, or if there's some sort of random forcing in the model, the statistics there. And now, okay, so there's sort of this approach of physicists and engineers, and I want to emphasize that there are physicists that take mathematician approach and mathematician that take physicist. So in general, attacking these problems is not really a person-specific thing, but just general approaches. So what people here typically do is they perform, very accurate experiments and simulations that inform what's actually going on, because the system is so complicated that without actually looking at it, one would make no progress. They often also provide phenomenological theories that are based on either some heuristic principles, sometimes informed by the equation, sometimes not, and are sometimes a result of fitting data. And it's often typical that they won't make very precise mathematical statements because maybe they're too smart to do so, because it's often very hard to prove, and typically you can give counterexamples to precise statements. So they shy away from doing that.
So engineers really use these equations for their modeling. For instance, you mentioned airplane several times, so
yeah,
do people model this really?
Yes, so, well, there's a whole discussion behind that, but in engineering, the idea is that this equation or some appropriate modification of it to incorporate other effects like boundary and maybe other physical important things are the true behavior. That's their philosophy. But often when they do simulations, it's practically impossible to use these equations, and namely to really accurately resolve solutions of these equations because of the fine scales that they develop on a modern day computer. I mean, at the Reynolds numbers that they need it for. So for example, in airplanes, like an airplane company, my understanding is that the Reynolds numbers that they would need to compute in order to describe, say, the forces on the plane or the wake are far beyond what current computers can handle. And so in the engineering world, there's yet another bullet point here. which is about modeling essentially the effect of neglecting the small scale of the velocity field on the dynamics of the large scale. And that's, there's a whole field of solving the so-called closure problem, which is exactly this issue. And I won't talk much about that at all because there are essentially no theoretical result that one can produce in this system that can inform it. But there are actually complementary systems, maybe the subject of homogenization, other equations in which you actually can understand this sort of neglecting the small scales at the expense of adding additional terms to the large scale equation.
So could I just say, this connects with the word renormalization in the sense that Falkovich has this beautiful expression called, what is the memory of renormalization, which means when you average the fine scales to get an average coarser scale, what properties of the fine scale are consistently mirrored in the coarse scale? So for him, and going all the way down, even beyond computers, theoretically, this is the memory of renormalization, so, which is sort of the subject of the seminar. So it's exactly in this area of what you can know from the coarse scale about the fine scale, which fits with the name of the seminar, I think. Yeah.
I think that's true. Yeah, unfortunately, I don't have too much to say about it, but I agree that that's philosophically, I think, a close connection. Okay, so mathematicians, on the other hand, they try to prove things, formulate, first of all, precise questions and prove things from first principles, from the equations. Sometimes their proofs, and this is sort of not so common in mathematics typically, but sometimes the proofs are of a conditional nature. They rely on precisely formulating some experimental fact and deducing precise consequences of that fact that could then be experimentally tested. So in a way, certain mathematicians can provide or can play the role of a physicist in that sense. But also in general, a mathematician's job is to identify certain constraints of solutions in order for them to be either physical or observable, to understand how the PDE connects with the phenomenon. Okay. Okay, I'm going super slow, actually. It's like 3 minutes till the end, unfortunately, but I can continue as long as people are happy to stay. So let me...
Don't rush, don't rush. You're going in a good pace.
This is very good. It's very good.
Okay. So let me now make just some remark about observables or averages. So this is an idealized, theoretician setup for the problem, and this is often what people do in physics community and also the mathematics community. So one wants to achieve some sort of permanent regime for the flow, to set up a so-called statistical steady state. And to do that, typically you drive the fluid by a body force, a force that acts at large scales, like a big stirring, like a spoon in a pot or something like that. And then the fluid, as we'll discuss hopefully at length later, has a mechanism by which it cascades this energy from the large scale down to the smaller scales, at least in 3 dimensions. And this force, is typically taken to be either autonomous, independent of time. This is a simple setting in which many sort of dynamical systems results can be ported over from finite to infinite dimensions. Or it can be white noise in time. This is another simplifying assumption on the temporal dependence of the force. And there are a number of results, some recent, some not so recent, on behavior of uniqueness of ergodic invariant measure and behavior of solutions of the equation with that forcing. So all of those results are 2-dimensional. So far, there's no such general theory in 3 dimensions. Right, so, and then what one is, so once you have this notion of some statistically steady state where you can take either long time averages or ensemble averages in these two situations, then what are you interested in? Well, so then which are the observables that you care about? So typically these are things like kinetic energy or dissipation rate and structure functions. These are things I'll define shortly, or energy spectrum, again, I'll define shortly. These are properties of the flow which are of interest for engineering applications or just theoretical interest. These are the types of things that are usually global objects, average over the domain, or again, average over time and ensemble. This is the type of thing you want to predict. Right, so I sort of said this in words before, but in the case of the autonomous force, you do have this notion of an attractor for the dynamics, which we may talk more about in lecture 3. And there you define these observables by long time averages. So this is observing the solution close to the attractor. Or if you have this noisy force or even noisy initial conditions, one can think of a statistical mechanics approach where you have ensemble averages in the steady state, and you define instead these averaged observables by averaging over some ergodic invariant measure. And the ergodic hypothesis, which has not been proved in these situations, is that these two concepts agree, that you can compute these observables in either way and you would get the same. So in practice, just again to connect with what people do, there's a couple of remarks that are in order. First of all, you can never really compute this long time limit. You only average over a finite window. And typically what people do is if you're doing a simulation, you sort of stir up your flow. You wait until you observe empirically some sort of statistical equilibrium defined by you. And then you start a finite time window average in that state in order to approximate this. But in doing so, actually, you can sort of think about the problem as one that lives on a finite time interval, but has initial data or forcing that becomes very rough. So this is in connection with something maybe we'll talk about later. So it's important to just to have this in mind. And also, if you're computing things like derivatives, like as we saw, the dissipation of, I don't know if we saw that yet, actually, sorry, but the certain of these observables involve spatial derivatives of the flow. If you have like a wind tunnel and you can't put probes everywhere to measure different velocities at different points, you appeal to this Taylor hypothesis, which is a relationship between time lags and spatial lags by a mean flow. So this is all to qualify to say that what we can observe and what we can theoretically discuss are often two different things, and even it's very difficult to rigorously relate them many times. So whenever one looks at data, you have to keep this in mind when making comparisons with theory. Okay, so finally, we can start talking about sort of the most basic phenomenon in fully developed turbulence that motivated Kolmogorov's 1941 theory. And so this is termed the zeroth law of turbulence because of its foundational character. And it's the observation that the energy dissipation, which is due solely to viscosity, as we saw for Euler, energy is conserved. So solely due to viscosity, the energy dissipation remains non-vanishing in the limit as viscosity goes to 0, or said another way, Reynolds number goes to infinity. And so I'm going to explain that, but for now, let's return back to the equation and just try to understand, how to formulate it. So, okay, for these equations, the Navier-Stokes equations, when you're in dimensions greater than or equal to 3, in particular, not 2 dimensions, then there's only one known a priori conserved quantity, or controlled quantity rather, which is the energy. So if you do a similar calculation to the one we did on page 1, you can compute the rate of change of kinetic energy of the flow. And here I've just written it in its local form. So there's a total spatial divergence. This is representing the flux or the motion, like the moving the kinetic energy around the domain, but there's no net contribution once you integrate over space. And then there's a dissipation effect due to the viscosity. So that takes the form of viscosity times the gradient of u square. And then there's the work done on the fluid by the force in general setting. So if the solution is smooth enough to do these manipulations, then the rate of change of total energy is just equal to the dissipated. I mean, it's reduced by the viscosity in this form, and its input to the flow by the force like this.
What happens if the function is not smooth?
Well, actually, so the anomalous dissipation, which I'll get to in a second, in fact requires that. If the function is not smooth, then the manipulations that you do to write the energy balance in this form are no longer valid. And in fact, this is essentially the main mechanism for what we observe about turbulent cascades being efficient at very small scales. So this is a fundamental point, and we're going to talk about it at length. Yeah. But okay. So whenever you have smoothness, and it turns out in a second I'll explain slightly more general setting, this balance here of the energy gives control of the solution in this space. I mean, okay. So the point is that this object right here is related to the sup norm in time, L2 norm in space of the velocity field u, just a square of that. This dissipation right here is related to the H1 norm, so it's one derivative in L2, and integrated in time, so L2 in time, because when you integrate this equation, you get 0 to t here, so that gives you the sup in that, and then the L2 in this. So from this balance, you can derive a bound for the solution, or bound for these particular norms on the solution. And actually, one of the foundational results in Navier-Stokes is that this observation can be translated to producing solutions that live for all time. So this was an observation of Leray, its foundation of the theory, that says that you can construct global weak solutions that live in this class by an approximation scheme. So I'll tell you what his approximation scheme was on the next slide, combined with a compactness argument. And then you have essentially a solution of this equation here in the sense of distribution. So you integrate against compactly supported smooth test function and demand that that integral form be satisfied. Again, I'll write things like this down shortly. But moreover, instead of having an equality here, you have an inequality. So Leray solutions lose energy like this and gain energy like that, but there could be additional sources of energy loss if the solution somehow becomes singular in finite time. And of course, resolving whether or not these solutions become singular in finite time is a major open problem. Doing so, if the initial data is smooth, is the millennium problem. So this is the famous problem about Navier-Stokes. But even for initial data that's just L2, which is all you need to define these Leray solutions, there's a question. And so this is a major open area, but I won't talk much about it. For now, what's important to note is that you have this energy inequality. And just a quick remark, Shinbrat proved that if you knew somehow that your velocity was actually L4 in space-time, then by interpolation you have essentially a third of a derivative in L3, which is enough to justify equality. And why that's enough, it's actually more than enough, why that's enough will be explained at length shortly. Is there a question?
So we are talking about local solutions, or what
These
solution?
these are global in time solutions.
So in dimension 3, everything works still.
Yeah. In any dimension, in fact, you have these
Any
global in time. Yeah, but they're not
So
classical solutions. Yeah.
So it's just the question is about developing singularities in finite time. So time, I mean, so
Right.
the solutions exist globally, but the question is whether they have singularities or not. Yeah, that is.
Yeah. So for Leray solutions, you can start with singular data, and certainly in the sense that the data need only be L2. So the classical question, which maybe you've heard many times, is whether if you start with smooth data, you develop a singularity in finite time. And then there's this statement that even if your data is just finite energy, you can give notion to a solution for all time. And the major open question at the level of these solutions is whether or not they are unique. And so it's unclear whether they're unique. And actually, there's at the moment it's not clear even if, like, for example, if you're in this space, you have equality in the energy, but it's still not known if you're unique. So there's a difference between the uniqueness class, and there's a lot of work on what conditions one would need to impose on the velocity for it to be unique, but so far none of them follow directly from the equation. They're just things you assume about the solution, then it's unique. Yeah. I should add that if you had a uniqueness theorem for Leray solutions, then in a sense that would be a good positive answer to the issue of whether or not Navier-Stokes would be a good description of motion of fluids. So there are results, the ones I mentioned about the derivation before, that are actually saying that you converge to Leray weak solutions of the Navier-Stokes equation. You don't need classical solution. So if you had uniqueness of this object, then it would be the description of the hydrodynamic limit of these particle systems in which you can prove those results. But that's an open question. So
just one question. So what is the physical interpretation of having inequality instead of equality when you've got a weak solution?
Right, yeah, so actually I'm about to talk about this. So what's known about the dynamics of the energy is actually due to Duchamp and Robert. They write down the same equation I just wrote down, except there's this extra term here, d of u. So d of u is a distribution that they define. It's defined right here. I'll get to that in a second, which is a non-negative distribution. So it can only, like I said, remove energy from the flow. And the physical interpretation is that if the Leray solution develops a suitably bad singularity, this contribution can be a positive due to the fine scale that develops as a result of that singularity. Okay, and so actually this distribution has a name. I mean, it has a parallel in the physics literature from long ago. So this is Kármán-Haworth-Monin relation. And you can see that the structure of this distribution here is something that's cubic in increments of the velocity. So when I write delta r of u, what I mean is I take u at a given point x, I add r, some vector to it, and I take the difference between u at that point x. So it's an increment. And there's a standard modifier that's scaled with L. So you have some compactly supported bump function, and then you rescale it so it lives at the scale L. So when you take derivative of this, you get essentially 1 over L from that scale. That's the size of the gradient of this object living at scale L. So you can see that this whole thing is on the order of delta LU cubed divided by L, by what I just said. And so now you can see why that 1/3 of a derivative was critical for showing that this wouldn't be there. So that was Schönbrott's result. because if you had essentially a third of a derivative, this contribution would be negligible. I'm going to again talk about this at length shortly. But actually, this is yeah.
So just maybe in the coming 5 minutes, find a good moment
Oh,
to,
okay.
to
Okay.
stop.
Yeah. Okay. So let me just go to. So this distribution is non-negative. There's a simple argument to show it. I'm going to just skip it. Let me just show you roughly how they arrived at this and how the physicists before them arrived at this. So let's just focus on the nonlinear term, because what this distribution represents is how the nonlinearity passes energy through to infinitesimal scale. It's quantifying that effect. And in order to study the behavior of the energy for these rough, weak solutions, one needs to introduce some sort of regularization to actually study its behavior. So we'll use what's called, I think, in the physics literature, a point split regularization, where you approximate the energy by taking the velocity at 2 different points and then sending those points together. So to make this rigorous, you take the velocity at 2 different points, but actually you mollify, so you just convolve one of the velocity fields and multiply it together. So what that corresponds to is taking that point split quantity and integrating it against an arbitrary scaled mollifier in R. And as L goes to 0, just if this velocity field is L2, this will converge to the physical energy. So now all we have to do to understand the behavior of the energy, and in particular the defect from the nonlinearity, is to derive an equation for this point split kinetic energy, UU prime. And okay, it's a calculation. Maybe I'll just focus on the main parts. So you get an equation for this by just multiplying one equation for u by u prime, and then multiply the equation for u prime by u. Then you start manipulating things. Whenever we see a total spatial divergence, I'm going to forget about it. That's not important for the global balance of the energy. I'm only interested here in the effect of that distribution, which cannot be of this form. This form would have no net contribution. So you work out that this equals these 2 terms in blue. Those terms in blue, you do some manipulation until you see. Okay, I'll skip the details, but until you actually see that the main contribution here is a divergence in the scale, namely divergence in R, the separation vector of this cubic quantity. And you have a similar term, but a divergence in X, which gets lumped together with this one. So now you see that this point split energy has this scale divergence term, which ends up converging in the sense of distributions to this D that Duchamp and Robert introduce, and the spatial flux, which is part of the balance that we don't care about, at least on average. So maybe I'll actually stop there, and I'll say that next time I'm going to discuss how essentially this distribution plays a role in Kolmogorov's picture of the energy cascade and turbulence, and then later Onsager's ideas about really making that into some precise framework that you can think about purely mathematically. And yeah, we'll go from there. Sorry for taking so long. Yeah.
Thank you.
Questions, comments?
So did Kolmogorov know this distribution? So
in a way, yes. So this distribution, maybe you've heard of this Kolmogorov 4/5 law.
yes.
This distribution essentially captures that 4/5 law. I mean, and I'll describe that. Yeah.
Oh, I have a question. So I'm intrigued by it. You sort of get a U cubed. You get a cubic
Yes.
thing.
Yes.
So,
It's like a U cubed over L over this is like a length scale, and there's U cubed or delta U cubed. Yeah.
so it's like it's ignoring the absolute value same. It's like the cube of the derivative, the change. What is the delta sub r?
It's like the ignoring absolute value. It's like this. This is heuristically what this is. You distribute one derivative over three things, so it's like this.
So the L cube norm of the third derivative. And then, so this is there. I mean, there's sort of a distribution that carries this information.
Yeah.
Like
And it's this
kind of fractal set of low Hausdorff dimension, because I know they have precise estimates. The Leray singularities are like less than dimension a half or something, right? I mean, in some very.
That's right. That's right. So for Navier-Stokes, absolutely, there are these results that characterize the support of singularity of Leray solution, and it's as you say.
I said something very vague. So what is it? What is it? Just how do you know how big it is? It doesn't use the usual definition of Hausdorff dimension because it's
yeah, there are different results
the
depending.
Factor and the time factor do differently, but
right. So I think the result in terms of the usual Hausdorff dimension is in space time it's less than 1. So the singularity, if it exists, has to sort of blip on and off. It can't be on a continuous segment in space time.
So it's like an arc in space time. At worst.
It can't be an arc. I mean, it has to be strictly less than 1.
Oh, I see. So it's like a Cantor set in space time.
Yeah.
So this distribution lives on a kind of a totally disconnected set.
Yeah.
Hausdorff dimension less than 1 in space in 4 dimensions. Wow.
So could you say a few informal qualitative words about the meaning of this anomalous dissipation of energy, about this?
Yeah.
You have a graph to show them? There's great graphs.
I do. Yeah. If you give me 1 minute, I can just show you the graphs, and then so you have the rate of change of energy is now including this distribution we just talked about, viscous dissipation, and then the work done by the force. So let's forget about the force a second. I mean, just the dissipation is the cumulative effect of this distribution and the viscous dissipation. So let's just call epsilon the total dissipation of energy due to either singularity or viscosity. Now, this 0th law of turbulence is the precise statement that this object is bounded away from 0 uniformly in the viscosity. Okay. And let's just call the lim of that epsilon without a viscosity to indicate you've already taken that limit. Now, here are the graphs. So this is from Srinivas in 1998. Here is epsilon normalized by the large scale of the flow and a typical velocity scale. So this is a non-dimensional number. Here you can see just as you increase Reynolds number, this going to a constant. Which constant depends on which precise setting, but in all these different settings, compiling, I think, numerical data, you see it goes to a constant roughly. And here's another paper, measures the same quantity, just a different name here, from experiment. And again, you can see at large values of this Reynolds number, it tending to a constant. That's the content of this anomalous dissipation.
Wait. So I think, so in other words, you would expect the graph to go, if you didn't have this, just these loss of energy because of some singularity, you would expect the graph to go to 0 as the viscosity goes to 0.
Exactly. And let me also emphasize the fact that.
Wait, let me just finish the sentence. And then, so you're saying that this horizontal line could be explained by the distribution that you were talking about.
Yeah, except not at so that distribution lives at what I would call finite Reynolds numbers. For a fixed viscosity, there's that distribution. But what explains this is actually the sort of in the limit as viscosity goes to 0, there's a distribution that's just like the one I wrote down that's responsible for carrying the energy out of the flow through 0 length scale. And that's the explanation of how this happens.
So these distributions have a limit as nu goes to 0. That's what you're saying. So there is.
Yeah. So that statement is almost proved. I mean, in a certain sense, if you assume, you have to assume that there's some compactness of the family of Navier-Stokes solutions. So in particular, and I'll describe this a little bit. Like there are some, we don't know that a priori, but under very mild assumptions that are borne out by the data, it appears that that's true. And then in that case, the distributions have a limit, and the energy due to this heating of the fluid at positive viscosity matches directly the energy that's forced out of the fluid by the nonlinearity. So that U cubed over L is the nonlinearity moving energy out of the fluid through 0 length.
So, and what is measured in these experiments? So how these experiments are done? So
yeah, right. So the experiments, here's an example of what you would do in a wind tunnel. If you have, so you have a probe, a hot wire probe that has some length scale associated to it. And as the wind passes, the velocity induces a current, which you can then use to measure by temperature fluctuations, the relative speeds of the velocity at the 2 different points on the probe. That is then used to get information on increments of the velocity at the scale of the probe, which you approximate the derivative of the velocity by, so that you can get information on this dissipation. So that's what you typically do experimentally. You translate, and it's always resting under the assumption that there's some sort of ergodicity, so that if you measure a time series at one point with one probe, then, and you do a long time average, that's qualitatively the same as doing, a spatial average. And so, right, so, yeah.
So to increase the Reynolds number, you just increase the scale. That's what it is. Or
in something like a wind tunnel, you can increase the flow velocity. So the Reynolds number is the typical velocity UL over nu. So you could increase it in general by either decreasing the kinematic viscosity. Yeah. And actually, by the way, there's an experiment in Germany, in Göttingen, where they actually changed the Reynolds number by decreasing the kinematic viscosity. And the way they do that is they have this toroidal domain, it's actually sulfur hexafluoride fluid inside it, and they pressurize it. The kinematic viscosity is actually a certain coefficient divided by the density of the flow. So if you pressurize it, you're increasing the density, and you can change that parameter just by doing that. It's still roughly constant, but you can change that. And that's how they change the Reynolds number. But it's very situation dependent how you do that.
Okay.
The distribution D of U is infinitesimally invariant by rotations, no? Or
right. So so actually, maybe we'll talk about that next time. So I'm going to relate D of U to something that's actually an average over directions of the separation vector. So it is certainly invariant, but we can talk about that next time.
So just to kind of summarize the whole math and the clay problem and everything, you could imagine somebody the Ray proved these weak solutions exist with the energy. Somebody else, let's say our grandsons, will prove they're unique. And then their great-grandsons will prove this distribution is really there, and it amounts for this graph that you observe. And you would really have a nice theoretical picture of the whole equation there. And somebody proves the ergodic hypothesis, et cetera, et cetera. So then you would have a theory that would back up what's observed.
That's the aim. Yeah, that's the aim. I think your timeline is very optimistic, but that's the aim.
No, but I mean, if, I just said if, you know.
Yeah. Okay. Yeah.
It's simple to list those ifs. I mean,
I agree. So actually, in a couple of slides, which I'll do on Friday, I'll do exactly those ifs. I mean, I'll sort of spell out what I consider to be the mathematical goal of, providing a rigorous foundation to these observations.
and would the list of observations be then restricted? Is there some theoretical reason why this is the observations that are studied now? Maybe you haven't mentioned them all. Is a complete list of what the theory allows you to study?
I'm not quite sure what you mean.
Well, I mean, you have this anomalous dissipation rate's been discovered, right? Are there other things that might be discovered in the future, which would also be part of the theory? Or is there some reason to believe a certain small list of observables is kind of complete in this statistical picture?
There are other things that eventually one would like to understand theoretically. So one of those things I think of great interest is understanding how nearby solutions deviate in finite times as Reynolds number is increased. So a remarkable thing that's observed, and this was done by Kreichnen and collaborators, with Kreichnen and Leith, it's observed that if you take two solutions of the Navier-Stokes equations, I'm paraphrasing, they didn't actually do this, but two solutions that are in some small neighborhood of each other, you can even make that neighborhood smaller as the Reynolds number increases. In a finite time, independent of anything, those two solutions will separate in L2, so in the energy space, to a distance that's independent of how far they started in the first place.
Or how close they started.
Yeah, how close, exactly.
You make them much closer and it's still they get it 1 unit apart, say. It doesn't matter.
Yes. Yes.
This is observed in weather balloons, I think, too. Yeah, I heard.
Yeah. So the same statement is also true for Lagrangian particles, which is like a weather balloon. But so it's a difference between this nearby separation of fluid trajectories and nearby separation of fluid solutions. So they're both observed, in fact, and one would like to understand both of them.
So that suggests there's a lot of things you cannot measure from the initial condition.
There's certainly a lot of things that you can't hope to predict, maybe like pathwise evolution, but you can still hope that some averages are independent of particular solution paths, and they are determined. It can be determined, but yeah.
Yes.
Other questions, comments? If not, let's thank the speaker again.
Thank you, Theo.